In this video, we're going to revisit spanning sets and linear independent spanning sets in terms of vector spaces. Suppose V is a vector space, then the subspace S, which is a subspace of, our vector space, is a basis if and only if it is linearly independent and it spans all of V. So a basis is a linear independent spanning set for a vector space. Before we had talked about spanning sets, but they didn't necessarily have to be linearly independent. We started building that foundation of it wanting to be linear independent. Now we say we want it to be linear independent because we want it to be a basis. So the definition of a standard unit vector, we talked about this before, but let's just review this. We talked about this in the orthogonal set. We denote it as being EI or EJ, where there is a 1 in that position and then zeros everywhere else. So if we're talking about in 3 space, it would be 1, 0, 0, and then it would be 0, 1, 0, and then the last one would be 0, 0, 1. And that would be the 3 standard unit vectors in 3 space. So of course this is E sub 1, E sub 2, and E sub 3 because of the positions that they're in. So we get this theorem. The proof is in your book for your viewing pleasure, and it says the set of standard unit vectors in the complex, which of course is in the real, is a basis for that vector space. So this that I wrote right up here, this would be the basis for R3 because I have 3 vectors, 3 positions, and 3 of the standard unit vectors. So if I'm trying to determine whether or not my 4 vectors here are, so we let S be a subspace and R4, so we're in real number entries where I've got 4 entries per vector. We want to span by this. And what we're trying to determine is whether or not these form, or what the basis would be. I guess I should ask that, what is the basis? Because that's kind of important. The basis of S. So I have 2 ways of doing it. The first way is I go ahead and just put those 3 vectors into a matrix, reduced row echelon, and I get this coming out. And I know that wherever I have a pivot, my pivot columns, which is the first and the second pivot columns, those will be my independent vectors. And so my choice for the appropriate choice for my basis, again, would be the first and second vectors. Alternately, we know from previous theorems that row equivalent matrices have identical row spaces, and non-zero rows of a matrix in reduced row echelon form a basis for the row space. So if I take that same set of vectors and I write it as rows instead of columns, I would get this matrix. If I then did the reduced row echelon form, I'm going to get this matrix B. It's equivalent. Not equal, but equivalent. Then we know that my first row and my second row, because they're the ones with the pivots, would form my basis. Now these don't look like they're the same, but if you actually continued to put in the zeros and ones in the appropriate places, these would actually produce the same values if you did the orthogonal of these vectors. So then we get this next theorem, which says columns of non-singular matrices are bases, which we kind of knew because when we were looking at our matrices, and we know that if they're non-singular, they end up becoming the identity matrix, I sub n. So we know that if we're in I sub n, each one of those columns are the standard unit vectors. From that, we get this next theorem, which says if A is a square matrix of size n, and then these are all equivalent. I could say that it's non-singular. If it says it's non-singular, then it's going to reduce row to the identity matrix. It also says that the null space of A contains the 0 vector. In other words, there's no other way to get from point A to point B unless everything was equal to 0. All of my scalar multiplications would have to be 0. The linear systems has a unique solution. We knew that too. The columns of A are linearly independent. A is invertible. The column space of A is in Cn. Column space of A is in Cn. And the columns of A form a basis for Cn. It's square, remember, so I don't have to worry about the M part, just the N part. The last couple of theorems that we get in this section is that we know from previous sections orthogonal sets are linearly independent, and orthonormal sets are the vectors that have been scaled to a norm of 1. So basically, they're orthogonal vectors that have been scaled with a norm of 1. That then gives me these next couple of vectors, and the reason that we want to talk about orthonormal sets is because it's really good for some computations we're going to be doing later. So suppose B is these vectors as an orthonormal basis, then we know that our V1 and W and V1 that our W here is a vector of our subspace of our complex, and this is true for real. Using the inner product can be formed, W can be formed by using the inner product of these vectors. And lastly, let A be an n by n matrix and B be in these orthonormal basis for Cn. We define C as being the A matrix multiplied by each one of those vectors that are orthonormal. Then A is a unity matrix if and only if C is an orthonormal basis in the complex numbers with size n. Let's do a couple of examples here. So suppose that S is a subspace of R5, and we know it's R5 because I have 5 entries. I want to determine a basis for S. So the first thing I'm going to do is I'm going to put the columns into a vector, or into a matrix, and I'm going to reduced row echelon that. Now the only places in which I have pivots is my first and my third, so it is only my first and my third that are going to produce my basis. This basis will not span R5 because I don't have 5 vectors. I only have 2 vectors, and we know from previous that this means that my dimension is 2 because that's a number of vectors that I have that are linearly independent. Now let's take a look at this example in which I have the set of vectors, and I want it to expand it out so it spans all of R3. Right now, at most, if these are linearly independent, I'm only going to be able to span R2 because I only have 2 vectors. Remember, my dimension tells me how much I'm going to span. So I need a third vector. The way in which I add a third vector is I start out with my original 2 vectors, and then I augment on an identity matrix of size 3. Then I do the row reduced to echelon form, and what I end up with is I end up with a pivot in the first column, the second column, and this fourth column. So to expand out those first 2 vectors to make it span R3, I need 3 vectors, so 3 entries, and I did that again by augmenting on my identity matrix, reduced row echelon form, and I end up with my first column, my second column, and I ended up with this column after the augmentation. So here it is, and here it is, and that's why that was the vector that we needed to add for this. And that's pretty much it.